In this video lesson, we're going to take a look at expanding and factoring perfect squares. When we talk about perfect squares, we've already seen earlier in Chapter 3 that a perfect square has the exact same factor twice. Often we recognize perfect squares simply because they involve a squared. In order to factor perfect squares or to expand, it's helpful to recognize this pattern, which is hopefully already in your notes. If not, this is a good time to hit pause and copy it down. This pattern becomes a little bit easier to use once we see it in action. If we are asked to expand x adding 11 all squared, the first job is to connect this to our pattern. In this case, when we look at our expansion, there is 1x, so we're going to say that a is equal to 1. And the second piece is an 11, so we'll say that b is equal to 11. We need to know that 1 squared is 1, that 2 multiplied by 1 multiplied by 11 is 22, and we need to know that 11 squared is 121. All of this is work that you can consider mental math. In terms of showing your work, we get to go straight to a final answer. Our expanded form will involve 1x squared. If you'd like to write that 1 in, you certainly can, but you don't have to. We know what it means when we see a single x squared written down. The 2a times b, 2 multiplied by 1 multiplied by 11, we're going to have 22 x's, and our b squared part of 121 is the last part of the term. Let's begin this example considering our a and our b. Next, think about the different parts of your pattern. In this case, it's useful to remember that when we square -5, a negative multiplied by a negative becomes positive. Lastly, we're going to write down our expanded form. And keep in mind, this is all that you have to record. We're going to talk about 16 groups of a squared, and that variable comes from what's given in the problem. Subtracting 40 groups of a, again the variable in the problem, plus 25. Take a moment to hit pause and see if you can correctly expand this perfect square. This one's a little bit more challenging because of the two variables, but filling in our number pieces will work the same way. We're still going to talk about 36 as the coefficient for our first term, subtracting 84 somethings plus 49 more somethings. The first term involves an n, so in my expansion, the first piece will give us an n squared. The second term in our perfect square involves a p. My last term will involve p squared. And so actually in our 2ab term, we're looking at two groups of 6n multiplied by -7p. So this is -84 np. We fill that in, and once again, we finished our expansion. Keep in mind when we're talking about the perfect squares pattern can also be used for factoring. Keep in mind that you should always check for a common monomial factor first. This can often simplify problems. In this first example, when we look at the trinomial, it doesn't have a common monomial factor. There's only 1x squared, and x is not a part of every term. So we start to think about perfect squares. X squared is a perfect square, and 64 is a perfect square. Looking at this example, we have 1x squared. That 1 tells us that a squared is 1, so we would guess that the a term is also 1. The 64 is like our b squared term. We think that b squared is 64, which means we probably think that b is equal to 8. This is a good time to double check. 2 times a times b. In this case, that's a 16, which matches up to what we see in the original factoring. Now we can write down our perfect square factorization. Since a is 1, we could write that in if we want to, but we don't have to, and b is 8, our perfect square factorization is one group of x, or plain old x, plus 8, all squared. Taking a look at this factorization, I notice that each of these terms is even. In other words, there's a common factor of 2. So I'm going to start there. Once I factor out the 2, I notice that I have 1x squared, that's a perfect square, and I finish with a 4, that's a perfect square, so I'm going to test my perfect squares pattern. I think that a squared is 1, so the square root will be a equals 1, and I think that b squared is 4, so the square root b is 2. Now I'll check that middle term. Two groups of a times b does match up with what I have, so I'm ready to write down my fully factored form with the perfect square. And here's my final answer. Notice that the 2 we originally factored out is still part of this final answer. Here's our last example. It looks really scary and complicated, but we think about this in the same ways. 169y squared is a perfect square, and so is 16z squared. So let's try the pattern. We notice that 169 has a square root of 13, and 16 has a square root of 4. Double checking our 2 times a times b, we get 104, but I notice that it should be a negative 104. We make that happen by saying that our b value is negative. And now we write down our factored form. Since this example includes two variables, we're considering that y squared would come from 13y and 13y. We're considering that the z squared would come from negative 4z multiplied by negative 4z, and 13y's multiplying with negative 4z's will end up giving us those yz's that we expect.